Advanced techniques for fine-tuning LLM. We know this fine-tuning, it allows customizing LLMs on your data to significantly improve their performance on this domain-specific task. But naive fine-tuning methods can easily go wrong, which can degrade the model quality. So let's dig deep on advanced techniques and best practices for effectively fine-tuning LLMs, in which we will cover the common pitfalls to avoid during fine-tuning, what are the state-of-art training methodologies, architectures and tuning strategies, specialized techniques by model type, practical guidance, and emerging innovation. So let's start with the common pitfalls to avoid. First, it helps to understand the common mistakes that can easily derail your fine-tuning efforts. First is the insufficient training data. Now this we know LLM needs vast amount of data to learn effectively. So this fine tuning on small data set often leads to overfitting. As a rule of thumb, 1000 examples is an absolute minimum per task. Then unbalanced training sets. So this class and data set imbalances can bias the model. So ensure diversity in your data and handle this imbalanced classes with techniques like oversampling. Third is reusing public data. So LLMs are already trained on public data sets. When we are reusing the same data provides no new signal for the model, use only proprietary custom data. Next is poor prompt engineering. So this low quality prompt fails to provide the context needed for the LLM to generalize. Iteratively refined prompt and provide sufficient examples. And finally, not evaluating incrementally. So it failing to evaluate model quality during fine-tuning leads to nasty surprises. So test continuously as you fine-tune to catch issues early. Avoiding these common mistakes sets you up for effective fine-tuning. So let's cover state-of-art training methodologies. First is the reinforcement learning. So models provide actions to an environment and receive rewards in return to learn optimal policies, and it allows exploring compositional tasks. Then is the imitation learning, which learns from demonstrations by modeling expert examples and is effective for goal-oriented tasks defined by human behavior. Then self-training. So additional training signal comes from models' own predictions on unlabeled data using confidence coding, which creates a natural curriculum. Then meta-learning, which trains models to rapidly adapt based on small amounts of data and is well suited where limited task data is available. And finally, multitask learning, which trains models simultaneously on multiple tasks to leverage commonalities and improve generalization. So when we adopt these advanced techniques, it will take our fine tuning to the next level. So let's look at optimized model architecture. So first is the sparse model, which prunes the redundant connection in dense transformer models and reduce compute for faster fine tuning and inference. Then is the mixture of experts, which partitions model into sparsely activated expert subnet specialized on subnets of data and improve scaling. Then adapter layer, in which the small contextual parameters injected into base model layers, and it allows rapidly personalizing models without full training. Then memory layers, it augments the model with external memory, storing facts to leverage during fine tuning and improves the recall. And finally, it's a composable model, that is the individual model components trained separately then combined, which allows the component reuse across tasks and enhances the versatility. So adjusting architecture expands what is trainable given resource constraint. So next we'll explore the tuning strategies. So how you fine tune is just as important as what you fine tune. So this key tuning strategies include gradual unfreezing, in which we systematically unfreeze the lower layers of model for fine tuning and retains the general knowledge while adapting. Second is discriminative fine tuning. Here we are only updating certain layers identical as most influential target task, and it limits destructive changes to pre-trained weights. Next is multitask knowledge distillation, where jointly fine-tune on multiple goals using soft target outputs to retain broad capabilities. And then a Bayesian meta learning, so it learns optimal fine-tuning hyperparameters like learning rates using probabilistic framework. And finally, it's a catastrophic forgetting mitigation, which leverage replay, sparse updates, and modular architectures to avoid overriding and pre-trained knowledge. So when the strategic tuning maintains a model's broad intelligence while sharply domain performance, there must be certain specialized techniques by model type. So the first technique is transformer models. So here ablation studies validate contributing layers, then gradual unfreezing, adapter injections, and multitask knowledge distillation is used. Then we have memory augmented models, so where attention over memories are used to reinforce relevant knowledge and cache this fine-tune memories for retention and grow memories incrementally versus full retraining. Then we have sparse models, so where we fine-tune with proxy task to select important connections and redensify strategically important subnets, and model pruning is as continuous process as interleaved with training. Then we have multi-model models. So multi-modality is used to avoid overfitting in incomplete data, and this cross-model distillation to transfer knowledge across modalities. Next, let's evaluate this fine-tuned models. So first approach is the quantitative evaluation. So here perplexity, accuracy, F1 and other matrices are used. Then we have confusion matrices. Then we have statistical tests. Then next is qualitative evaluation. So here manual review by domain experts is done to check creativity, relevance, fluency. Then A/B testing is done on sample use cases, and then user studies are used to measure satisfaction on the real task. Then the robustness testing, here stress test with adversarial examples and edge cases are used. And we